Hi everyone, I hope everyone are fine. Welcome back to Sri Sampath Vinayaka Learn Easy channel. Today we are going to discuss the chapter functions. Before going to discuss about the functions, we are going to know about what is Cartesian product, what is a relation. Okay, now then after we are going to know what is a function. Now we are going to discuss Cartesian product. For finding that Cartesian product, I need two non-empty sets. Okay, I'm going to explain you what is Cartesian product, then you are going to know now how to write the Cartesian product. For writing Cartesian product, I need two non-empty sets. So let A comma B are two non-empty sets. Okay, Nama? Then the Cartesian product of A comma B is expressed as A cross B. Okay, now is written as A comma B such that A belongs to A comma B belongs to B. This is the Cartesian product. Okay, this is the set builder form of a Cartesian product. That means A comma B here is known as ordered pair. So A cross B is the set of all ordered pairs where this A belongs to A and B belongs to B. That is the definition we are going to write. See, Cartesian product means let A comma B are two non-empty sets, then the set of all ordered pairs such that this A belongs to A and B belongs to B is called Cartesian product of that A and B. So that we are going to express as A cross B is equal to A comma B. This is an ordered pair such that A belongs to A, B belongs to B. We are going to write all the possible ordered pairs into this set. That special set is known as Cartesian product of A comma B, and it is represented as A cross B, A into B, and it is going to be pronounced as A cross B. Okay, understand? With one example we are going to see. See, A comma B, let these are the two non-empty sets. Okay, if I am going to write the all possible ordered pairs here. Okay, what are the possible ordered pairs we are going to get into this A cross B? C ones. This one is mapped with P and this one is mapped with Q. So 1P and 1Q. With 1 I am going to write these two. I may write again 2P, 2Q. 2P, 2Q. Yes, I may write 3P, 3Q, 3P, 3Q. So these are only the possible ordered pairs I am going to arrange in the given two sets A and B. Okay, so that means see how many ordered pairs I am going to get into this set? 1P, 1Q, 2P, 2Q, 3P, 3Q. Totally I got 6 ordered pairs into this. That means the total number of elements in the A cross B, that means in the Cartesian product, is said as the product of the number of elements in the two non-empty sets. See, here I am having 3 elements. Here in this, that means number of A it is. Number of A is equal to 3 and number of B is equal to 2. So the total number of elements in the A cross B is expressed as 3 into 2. 3 into 2. That's why here I am going to write one note. If number of A is equal to M, number of B is equal to N, then number of A cross B is equal to M into N. So number of A cross B is equal to M into N. Now A cross B union C, let us suppose A cross B union C is given to us, then it is going to be expressed as A cross B union A cross C. Okay, similarly A cross B intersection C is equal to A cross B intersection A cross C. So remember this. Okay, these are the 3 note points we are going to remember in the concept of Cartesian product. One more thing, here this A comma B, ordered pair A comma B, here A is known as first coordinate, B is known as second coordinate. if listen ma, if two, see ma, if two ordered pairs are equal, then the first respective corresponding first coordinate is equal to first coordinate and second coordinate is equal to second coordinate ma. Okay, remember that. And if in a set we are having m elements, in the other set if I am having n elements, then in that A cross B I am going to have m into n elements. Okay, one more thing schema. A cross B is a set of ordered pairs where that first coordinate belongs to that first set and second coordinate belongs to that second set ma. Let A is equal to A, B, C, B is equal to P, Q. Okay, we know that A cross P is equal to AP, AQ, BP, BQ, CP, CQ. This is A cross B ma. If I want to write B cross A, then I have to interchange the ordered pairs ma. Okay, now the elements of the ordered pairs, that is PA, next QA, PB, QB, PC, QC. See ma, that is A cross B is not equal to B cross A. Okay, and here number of A is equal to 3 and number of B is equal to 2. Therefore, number of A cross P is equal to 3 into 2, that is equal to 6. Okay, Nama, see 1, 2, 3, 4, 5, 6. These are the 6 elements. So, this A cross B is having 6 elements. We know that in a set, if I am having 3 elements, see, this set A is having 3 elements. Then how many subsets it is having ma? So, 2 power 3. Okay. If number of A is equal to 3, better write some value ma. Okay, if number of A is equal to m, then number of subsets of A is equal to 2 power m. See ma, every subset of this A cross B is a relation. If I am going to write A comma P, B comma P into a set, let us take this one as R1. So this R1 is a subset of this A cross B. So it is a relation. Like that, if I am going to take any subset of this A cross B, then that is a relation. Then how many relations I am going to write to this A cross B? That depends on the number of subsets, how many it is having. So we know that this set A cross B is having 6 elements. Then this A cross B is going to have 2 power of 6 subsets ma. That is A cross B is having 2 power number of A cross B subsets. Okay nama? That is equal to 2 power A cross B is equal to 6. That is equal to 64 subsets this particular A cross B is having. All those 64 subsets are known as relations from this A to B. Understand ma? If I want to write all the 64 subsets, then all the 64 subsets are relations. See ma? Let A is equal to A comma B, B is equal to P. So these two are non-empty sets. Then A cross B is equal to this ma, AP, BP. Okay, I can write like this. Why? Because here it is having 2 elements, it is having 1 element. So A cross B is having 2 into 1, that is equal to 2 elements. Okay now, as we discussed, the number of subsets of A cross B are 2 power the number of elements in it. So 2 power 2, that is equal to 4 subsets we have. obtain empty set, singleton sets and the set itself. Okay, now we already discussed a subset of a Cartesian product. Subset of a Cartesian product is known as relation. That means, see ma, how many subsets it is having? 4 subsets. So all those 4 are relations or not, we are going to check. To become a relation, RE subset are equal to A cross B. Okay, and R is equal to, see ma, A comma B such that A belongs to A and B belongs to B. Okay, this is said to be a relation. Okay, see ma, coming to this empty set, okay, it is not a relation actually, but we are counting it into the number of relations. Why? Because every subset of the Cartesian product is known as relation. So that's why, see ma, so the number of relations from A to B actually we are going to express as 2 power m into n. But coming to the reality, the number of relations from A to B is 2 power mn minus 1 ma. Actually this is the right answer. But in many of the books you are going to find the number of relations from A to B is 2 power mn. Okay, now why I am reducing 1 means here this empty set. Okay, now this empty set is not a relation actually from A to B. Why? Because it is not going to satisfy the definition of the relation. See, relation is a subset of the Cartesian product where all the elements of the relation are ordered pairs. Okay, now A comma B such that A belongs to A and B belongs to B. Coming to this empty set, yes, Seema, this empty set is not a relation. Why? Because there is nothing present. Coming to this, yes, it is a relation. Why? Because see, all the elements of this set are like A comma P and A belongs to A and P belongs to B. So it is a relation. Okay, remember this. This is a very important bit. Every subset of the Cartesian product is a relation. Okay, so I am going to write one example from this. See ma, AP, okay na, BP. It is a subset or not ma to this? Yes, see, it is a subset. So it is a relation. Let us consider this as R1. R1 is a relation. Why? Because all the elements of this R1 are like ordered pairs, and here the first element belongs to A and second element belongs to B. So it is a relation. Understand ma? So we are going to discuss function ma. Okay. Actually we have to define different types of relations and different types of representations and classification of relations. But for discussing functions, these are not required to us now. Okay, now we are going to discuss the detailed concept of the relations in a different video ma. Relation is a subset of a Cartesian product. Relation is a set of ordered pairs also. So we are going to define the actual definition. Let A comma B are two non-empty sets and A cross B is its Cartesian product. Then R is said to be a relation from A to B if this R is subset are equal to A cross B. That is, R is defined as A comma B set of ordered pairs A comma B such that A belongs to A and B belongs to B ma. See, now these are the very important bits ma. If number of A is equal to M and number of B is equal to N, then number of A cross B is equal to number of A into number of B. That is M into N. We know that the number of subsets of any set is 2 power of the number of elements in it. 2 power M into N. Okay, we decided and we explained that every subset is a relation. So the number of relations from A to B is equal to these subsets ma. Okay, that is 2 power Mn. That is by formula. But coming to the reality, 2 power Mn minus 1 is the number of relations. Why? Because the empty set is not included here. Okay, but many of the textbooks are given as 2 power of Mn as the number of relations. But as we discussed earlier, that empty set is not a relation ma. Understand? See ma, let A is equal to 1, 2, 3, B is equal to 4, 5. Then A cross B is equal to, we know that. Okay, now if we are going to write this 1, 2, 3 and 4, 5, Okay, now it is A and it is B. 1 4 1 5, like the 2 4 2 5 3 4 3 5. Okay, we are going to write the relation like this. Okay, so A cross B is equal to this one. As we know that this A is having 3 elements and this B is having 2 elements. A cross B is going to have 6 elements. Okay, now as it is having 6 elements, it must have 2 power of 6 subsets. Okay, now. So by the formula, the number of relations are equal to the number of subsets. Therefore, the number of relations is equal to 2 power of 6. By formula, it is 2 power of 6, that is equal to 64. But in the reality, how many relations we are going to have? 64 minus 1, that is equal to 63 relations we are going to have. Why? Because empty set is not going to be considered as a relation. So see, now this 1 comma 4 is subset to this A cross B, so it is a relation. Now relation 2, 1 4 1 5 2 4, this is a subset of this A cross B, so it is a relation. It is a relation. Like that we are going to write 63 relations. Okay now. Okay, actually 64, but the empty set is not considered as a relation. So that's why 63 relations I am going to write. See here, if I am going to write all the first coordinates of a set into a new set, then that set is known as domain. What? Domain. Domain means all the first elements of a set is known as domain. So if for example R2's domain, if I am going to write domain of R2 1 2. Why? Because if I am going to write all the first elements here 1 1 2. So in a set we know that only once we are going to write the element. 1 2 is the domain. Image of R2. Image of R2. See, if I am going to place all the second coordinates of the relation into a set, then that is known as image set. Understand ma? So remember them. Okay, I am going to give you the definition. See ma, domain. Set of all the first elements of a relation is called domain of the relation. See, here the relation is 1 4 2 4 3 4. Why? Because this 1 4 2 4 3 4 is a subset of this A cross B. So domain means what we said, the first elements. What are the first elements of all the ordered pairs? 1 2 3. So this 1 2 3 comes into this set. Now this set is known as domain. Similarly, if we are going to place all the second elements of a relation into a set, then that newly formed set is known as range. So here what is the range ma? 4. Why? Because all these are having 4 as its second element. So the range of the relation is 4 ma. I am going to take one more relation. Let R2 is equal to 1 4 1 5 2 4 3 5. See ma. In this relation, tell me the domain. Domain D is equal to 1 2 3. Range R is equal to, okay na ma. If I am going to write range as R, then R is equal to 4 5. Okay. See ma. Here like this. Okay. So this is relation. Okay na ma. In the relations topic, we have to discuss different types of relations, how to represent relations, okay, what are the properties of relations, everything is there. But we are going to discuss it in a separate video ma. Now we are going to discuss about a function. See ma, function is nothing but a special relation ma. What is the speciality of that particular relation means, in any relation, if the first coordinate of any two ordered pairs are not same, then that relation is known as a function ma. In any relation, if no two ordered pairs are having the same first coordinate, then that relation is known as a function ma. Okay, now we are going to discuss the functions. Okay, I hope you understand. Function means a special relation ma. What is the speciality means, if no two ordered pairs of any relation are having the same first coordinate, okay na, then that particular relation is known as a function. Understand? If the first coordinates of any two ordered pairs are same, then that relation is not a function. Let us see. Here the first coordinates of this relation is 1, 2, 3. There is no same first coordinate. So this relation is a function. Coming to this, Seema. Here these two ordered pairs are having its first coordinate as 1. So it's not a function. Okay, if we are going to find at least one pair of ordered pairs whose first coordinates are same, then that's not a function. Understand ma? Seema, as we discussed, function means firstly we have to take two sets. Those two sets must be non-empty. That's why let A comma B be two non-empty sets. Then we have to consider a relation, and we discussed that that relation is said to be a function. Okay, now where there no two ordered pairs are going to have the same pre-image. Okay, see. So let A comma B be two non-empty sets. F is a relation. Firstly, we have to consider that F is a relation from A to B. Then this F is said to be a function. When it is going to obey, for every A belongs to A, there exists some B belongs to B, such that A comma B must be of the relation F. Then no two ordered pairs in F have the same first element. We discussed. Okay, now this is the specific nature of this relation. If it follows this specific nature, then that relation is said to be a function. So then F is called, that means F in the sense that relation F is called function. Okay, now from the set A to B. Or we may define that function as a relation F from A to B is said to be a function if every element in A associates with an element that is exactly one element with B. Okay, then that relation F is said to be a function. It is denoted by F is mapping from A to B. It is written like this, and it is going to be pronounced as F is mapping from A to B. Okay, na? Seema. Here some note points are there. The first note point, Seema. If A comma B is the ordered pair belongs to the function F, then that can be expressed as F of A is equal to B. That is, A is mapped to B. Okay, so that can be expressed as F of A is equal to B. And B is called the F image. This B is called F image of A. And this A is called the pre-image of B. A is called the pre-image of B. And this B is called F image of A. Understand? Remember them. Okay, that means this mapping, that means this ordered pair is expressed as F of A is equal to B. Understand ma? Now, and here we are going to call this A as independent variable, and this B is also dependent variable. Understand ma? That is note point 1. Coming to this note point 2, if F is mapping from A to B is a function, then A is called, this A is set A is called domain, and this B is called codomain. Okay ma? Remember these two names. Okay, here A is called domain, B is called codomain. Understand of the function F. See, let us take two examples, 2 or 3 examples. See ma, here, see ma, this is the function from A to B. See, this arrow marks indicates this is the function from A to B. See ma, here the relation F is a function because just observe ma, different elements of A are, that means each element of A are having exactly one mapping in B. Okay, see, all the elements of A are mapped with B, and there is no two ordered pairs with the same first coordinate. See, here the first coordinates are 1, 2, 3, 4. There is no two ordered pairs with the same first coordinate. So this is a function. Coming to this second example, see, this G is a relation from B to A actually. Okay, now I am going to express this is as a function. Why? Because see, this G is a function from B to A. This arrow mark indicates from B to A. See ma, B to A means we have to one search is there any element left in B. So no element is left in B. That means every element of B have a mapping with exactly one element of A. So see, okay, here in element, sorry, in set A, there may be some elements left. Here also this is the function from A to B, no? If you want to write 8 here, so here you may write. Okay, in the B you may have some extra elements. But if the function is from A to B, then in the A we are not going to leave even a single element. We have to map each and every element of A with exactly one element of B. Understand, ma? That's it. So these F and G both are functions. Now coming to this H, once see, ma. Here 1, 2, 2, 3, 4, 4, 1, 5. Is this relation H is a function, ma? So once observe this. It's not a function. Why? Because in this relation, see, ma, these two ordered pairs are having same first coordinate. Because of that, the relation H is not a function. Okay, now remember them. So here some representation, see, ma. 1 is mapped with 5, no? So f of 1 is equal to 5. F of 1 means 5. This f of 1 belongs to B. Okay? F of 2 is equal to also 5. That means this f of 2 belongs to B. Okay, Nama? Here see. G of 2 is equal to A. Okay? That means this G of 2 is an element of A. Okay? Remember the representations, ma. See, ma. Domain and codomain. As we discussed, if f is mapping from A to B, then A is said to be the domain of the function f and B is said to be the codomain of the function f. Okay, now actually how to write the domain if he is going to give you the function with ordered pairs. Okay, now if he is going to give you like this, f is mapping from A to B, then A is said to be the domain and B is said to be the codomain. It's good. But if he is going to give you a set, okay, now with ordered pairs, then the set of all the first elements of the given ordered pairs of the function is considered as a domain. That means the set of all the first elements of the ordered pairs of the given function. Now, range means the set of all the second elements of the given function is known as range. Okay, see. So, if f is mapping from A to B is a function, then set of all the images of the elements in its domain. Okay, now for the domain, what are the images we have to take? All those images if we are going to place in a set. That means f of A is a image we know. So, if we are going to write all the images in a set, then that set is known as f of capital A. This is said to be image set. Okay, now f of A such that A belongs to this A. This is the definition of range. Okay, range of a function is always subset or equal to the codomain. Understand? If f is mapping from A to B is a function and number of A is equal to x and number of B is equal to y, then the number of functions that can be defined from A to B are y power x. Okay, this is the important formula. Remember this one, ma. Okay, now we are going to consider some examples and we have to check whether those are functions or not, ma. See, let A is equal to 1, 2, 3, 4 and B is equal to set of 2, 3, 4, 5, 6. Okay, let us take f is a relation defined as f of x is equal to x plus 2. Okay, na? Initially that f of x is equal to x plus 2 is a relation. Now we are going to check whether it is a function or not. Let us find the ordered pairs of the given relation f of x is equal to x plus 2. For the domain, okay, now 1, 2, 3, 4, we have to find its images. For 1, if I am going to place 1 in the place of x, okay, now 1 plus 2 is equal to 3. So 1, 3 is a mapping. If I am going to place 2 in the place of x, then 2 plus 2 is equal to 4. 2, 4 is a mapping. If I am going to place 3, 3, 5. If I am going to place 4, 6. Okay, this is the obtained relation. Here see, ma, this relation is a function because all the elements of A are associated with exactly one element of B. Okay, that means no element left in A. That's why f is a function. Okay, and no two ordered pairs are having same first elements. Okay, now here the second example. See ma, set of -2, 2, 3, 4. Set of 4, 9, 16. See ma, here the relation is defined as f of x is equal to x square. Now I am going to find the ordered pairs of the relation f of x is equal to x square for the elements of the domain. Here the domain is my a, that is -2, 2, 3, 4 are the elements under the domain. So substitute these -2, 2, 3, 4 in this. If I am going to substitute -2 in the place of x, then I am going to get 4. -2, 4, 2, 4, 3, 9, 4, 16. These are the ordered pairs comes into this relation. Now see, this relation is a function. Why? Because every element of the domain A are associated with exactly one element of B. So this is a function ma. Now coming to this third example. See, here the set A is given as -1, 1, 2, 5. B is 1, 8, 1, 25. These are the two sets. Let us take the relation f as f of x is equal to x cube. Now find all the ordered pairs of that relation f of x is equal to x cube associated with the each and every element of A. See ma, if I am going to substitute this -1 here, then -1 whole cube is equal to -1. But to this -1, the image is -1, but that -1 is not in the set B, that means in the codomain. So this -1, for the element -1, there is no image. Okay, find the rest of the elements. For 1, 1. For 2, 8 is the image. For 5, the image is 125. But for the element -1 in the domain A, there is no pre-image in the codomain B. So because of that, it's not a function ma. Understand? See ma, now we are going to discuss the difference between relation and a function. Okay, see, every function is a relation, but every relation need not be a function. We know that. Why? Because a special type of relation is known as a function we described. Okay, the speciality is that specific nature of the relation is no two ordered pairs are going to have the same first coordinate. Okay, that is first specific nature. And the second specific nature is the domain of the given relation must be equal to the set A if it is defined from A to B. Okay, now if it is defined from x to y, then the domain must be equal to x. Then the relation becomes a function ma. Okay, see, every function is a relation, but every relation need not be a function. Now a relation f is mapping from A to B is called a function if it follows the two rules. The first one is the domain of the relation f is equal to A and no two different ordered pairs in the relation f have the same first coordinate. Okay, now then that relation is known as a function ma. Okay, now let us consider three relations defined on A to B. Okay, see, f is 1a, 2b, 3c, 4d. Now g is 1a, 2b, 3c. h is 1a, 1b, 2c, 3d, 4e. See ma, this f is a function or not we are going to check. For that we have to check its domain first. We have to check these two rules ma. So see, what is the domain here? Domain of the function. Domain of the function f is equal to 1, 2, 3, 4. This 1, 2, 3, 4 is nothing but A. So domain of f is A. First rule is satisfied. No two different ordered pairs have the same first coordinate. See ma, here no two different ordered pairs are having its first coordinates as same. So that's why f is going to be a function because it is satisfying these two rules. Coming to the next relation G. See ma, this relation G is a function or not we are going to check. Write the domain of G. Domain of G. Domain of G is 1, 2, 3. This is not equal to A ma. See, domain of G is not equal to A. Because of that, domain of A is not equal to A. Because of that, G is not a function. So the relation G is not a function here. Coming to H. See ma, here write the domain of H. Domain of H is equal to 1, 2, 3, 4. See, yes, the first rule is satisfied. Here the domain of H is equal to the domain A, that means set A. The second rule is no two different ordered pairs are going to have the same first coordinate. But here see ma, this 1A and 1B are the two ordered pairs which are with the same first coordinate 1. Because of that, here the H fails to satisfy the second condition. So H is not a function now. Understand ma? See ma, up to now we discussed how to check whether the given relation is a function or not. Now I am going to explain you how to check the given geometrical figure is going to be a function or not. Okay, see ma, let us suppose this is the coordinate plane and let us suppose this is the geometrical figure. Okay, this is the circle. To check whether it is a function or not, we have to draw a parallel line to the y-axis on the geometrical figure. See, if I am going to draw a parallel line to y-axis on the geometric figure, if it intersects the geometric figure at one place, then it is a function ma. But see, here it intersects in two different places. So that's why it's not a function. Understand ma? See, if I am going to draw a parallel lines here, okay, now it intersects the given curve at one point. So this is a function. Understand ma? Like this we are going to check. See ma, now we are going to discuss different functions and its domain and range ma. Okay, so see, the first function here we are going to write modulus function. We know that in that modulus, for the value of x, I may place any real number. Okay na? So the values which we are inserting for the value of x, okay, is known as domain. So in the place of x, I may write any real number. That is why, so the domain of the modulus function is R. And the answers which we are obtaining all are positives, including 0. So that's why from 0 to infinite is the range of the function modulus x. See, here this is box x. Box x means we know that it is an integer function. Box x. Box x means we know that. Okay, now we are going to place any real number in the place of x. Then we are going to write the closest integer. Okay, so that's why this box x, that means here we are going to insert any real number. So the values which we are inputting or which we are inserting are known as domain. So domain of this box x is real numbers ma. And the answers we are obtaining are integers. So that's why the range is z. Root x. We know that we are going to find the square root for only positive numbers. So that's why here I am going to place only positive values for x. That's why the values which we are placing are known as domain, no? So 0 to infinite I am going to place. So 0 to infinite is the domain. And range means we know that for the square root of any positive value, we are going to obtain positive values only. So the range is also 0 to infinite. See ma, nth root of x. In this nth root of x radical, this is radical function ma. In this radical, we are going to place any value for this x. That is maybe positive, negative or anything. Okay na? So, and the answers we are going to obtaining is also positive, negative, everything. So, the real numbers is the both domain and range for this function ma. 1 by root x. See ma, here we did root x. For square root, from 0 to infinite we are going to place. But if we are going to place 0 for the value of x, then root 0 is equal to 0, we know that, then it becomes 1 by 0. So 1 by 0 is not defined. Because of that, here in 1 by root x, okay now we are excluded with the element 0. So we are not going to use 0. So here I am not included that 0. So 0 to infinite is the domain for the value of 1 by root x. Okay. Now the values which we are going to obtain is also from 0 to infinite. Okay. Now 1 by x. The same rule we are going to use. 1 by x means I may use any value for x. But if I am going to use 0, then this 1 by 0 is undefined. Because of that, from the real numbers I am going to subtract or remove the 0. So the domain is all the real numbers except 0. Okay now. So then there we are going to get the image also all the real numbers except 0 ma. 1 by modulus x. So 1 by modulus x means we discussed it for modulus x, the domain is real numbers, but it is in 1 by x form. So that's why here we are not going to use 0. So r minus 0. So 0 to infinity is the range. See, a power x, exponential function. A power of x means I may place any value for x. So that's why here the domain is r, and whatever the values we are going to place in this power, I am going to obtain only positive values. That's why its range is 0 to infinite. See, log x, we know that we are going to place only positive values. Logarithms are going to be calculated for only positive values. So here I am going to write in the place of x 0 to infinite. 0 is also not defined. That is why we are not going to include this 0. Understood, ma? For the log function 0 is not included because log 0 is not defined. So only positive values we are going to place. Because of that the domain is 0 to infinite, and range may be any value, that is may be positive, negative. Okay na? That's why the range is real numbers. See, sine function, we know that sine function in the place of x I may write any real number, that means any degree. For any angle we will find the value of sine. Whatever the values we are going to place in the place of x, we are going to obtain only the answers as -1 to 1. Okay, that is if you are going to draw the graph of this so this is 0 to 1. Okay, now that is 1 to 0, again -1, like this graph is going to be. So that's why its range is always +1 to -1. Understand? That's why here the sine's range is -1 to +1, including all the 1 and -1. Now cos, here also the same. Okay, now I may place any value for the x, but the obtained values are always like this. Okay, that is again this is the range of -1 to 1. Now tan x, for the tan x I have to place any value of x except the odd multiples of 90. Okay, if I am going to place, listen, odd multiples of 90 in the place of x, okay, now those values are not defined. So that's why I have to remove those odd multiples. So then I am going to obtain tan's range as infinite. Okay, now why? Because see, real numbers know its values. This graph of tan x is like this. Okay, now that means see, its range is infinite. That means positive infinite, negative infinite. That is expressed as real numbers. Cot also similarly, but for cot I have to remove all the even multiples of 180. For secant x, r minus odd multiples of 90 we have to do. Why? Because again if I am going to place 90, its values are not defined. Okay, now cosecant x I have to remove all the multiples of 180. Okay, so the range is from -infinite to -1 including -1, and from 1 to infinite including 1. So in between this -1 to 1 values are not considered because of these values. Okay na? So I have to remove them. Inverse functions now. Sin inverse x. For sin x we obtained a range. No, that range is going to be the domain here. Okay na? Sin functions range is sin inverse domain. Similarly, cos functions range is cos inverse domain. Tan inverse, like that we are going to write the domains. It's clear now? So range of sine function, cos function, tan function, cosecant function, secant function, cot function becomes domain of its inverse functions. Understand? Then after we are going to find its range. Sin inverse x means -π/2 to π/2 is its a range. Okay na? Inverse in the sense you are going to get some angle values. Okay, those are the range. So here also cos inverse x range is from 0 to pi. Okay, tan inverse x -π/2 to π/2. Cosecant inverse x -π/2 to 0, excluding that 0, and from 0 to π/2. There also we have to exclude that 0. Okay, why? Because if we are going to place those zeros, these values are not going to be defined. Okay, now similarly, secant inverse x range is also from 0 to pi by 2. Pi by 2 is excluded again from pi by 2 to pi. Okay, that means pi by 2 value is excluded. Now see, here cot inverse x, its range is from 0 to pi mark. Okay, na? Here we are going to discuss the hyperbolic functions. Sin hx, its domain is R and range is also R. Here next cos hx. Cos hx's domain is again R mark and its range is from 1 to infinite, including that 1 mark. Understand? And now coming to this tan hx, its domain is R. That means in the place of x I may write any real number. Okay, na? And definitely its range is going to be minus 1 to 1 mark, excluding those ones. Okay, now cot hx, its domain is R minus the set of 0. That means we have to remove that 0 from the real numbers and I may place any value. Okay, then its range is from minus infinite to minus 1 x, excluding that minus 1, and 1 to infinite, there also we have to exclude that plus 1. Okay, or we may write real numbers minus set of closed values minus 1 to 1. Secant hx, its domain is real numbers and its range is from 0 to 1, including 0 and 1. See, next cosecant hx, real set of real numbers. Okay, now from the set of real numbers we are going to remove that 0, then its range is going to be the same. Understand, ma? So these are the different functions and its domains corresponding images. From this concept, definitely you are going to get 1 or 2 bits in your competitive exams, ma. Okay, these are very easy. Try to understand and try to remember, ma. Okay, thank you for watching. In the next video, we are going to discuss the different types of functions.